Alright, so in this next section, 2.6, we're going to look at transformation of functions. And what this means is, well, since we can't use the calculator again, how are we going to graph more complicated functions? So you can always graph a function by plotting enough points and then connecting the dots, and then you'll see the shape of it. But there are many times when you'll know very well what the graph of a particular function looks like. So you know how the graph of x squared looks like, for example. So if you know that, how can you use that to graph similar function without plotting too many points? So this is basically what we're going to do in this section. We'll discuss some ways to graph more complicated functions. So for example, if we want to find a quick way to graph the function f of x equals negative x plus 2 squared plus 5. So you know that this is a parabola, but exactly where is the vertex, or how does it look like exactly? Well, if you know enough about f of x equals x squared and what are each of these, what is this 2 doing, what is this 5 doing, then we can easily graph this function by knowing information about x squared. So we're saying we're transforming this parent or basic function x squared. We're doing something to it. We're moving it up or down, to the left, to the right, or reflecting it, we're stretching it, or compressing it. We're doing something to the parent function to get to another function. So the types of transformations we're going to talk about are rigid transformation. Rigid transformation changes the location of the function in the plane, so it moves it up or down, it moves it to the left, to the right, it reflects it over something, but it doesn't change the shape of the graph. A non-rigid transformation is going to change the size or the shape of the graph. So imagine if you have a piece of elastic and you just move that elastic up or down to the left or to the right, or that would be a rigid transformation. A non-rigid transformation is if you stretch it horizontally or if you stretch it vertically. Okay, so it's going to be very important that we know the basic functions or the parent functions. So you need to be familiar with quadratic function, cubic, square root, and absolute value, just the basic ones. So f of x equals x squared, you should have done it many times, enough to know that it looks like this. The vertex is at 0, 0, and then it's going to look like this. I'm still giving it points to see the shape, but you should know that x squared looks like this. And then the cubic function, f of x equals x cubed, you should remember that's the S-shaped function, and it's going to look like this. This is a power function with a positive exponent and odd. And then the square root function, that it looks like this. F of x equals square root of x. At 0, at 1, and at 4, the value is 2. And then the absolute value function, that's the V shape that I hope you remember. Okay, so knowing the parent function, the basic function, is going to allow us to move these around, stretch them, and get the graphs of more complicated looking functions. All right, so the first transformation that we're going to look at is a vertical transformation, which is a rigid transformation. So vertically, it just means that you shift the function, you move the function up or down. So if you have the graph of a function f of x, and if you add a constant, so c is just a constant, if you add a constant, then you obtain another function, which is just f of x moved up that many units. If you subtract a constant, so if you subtract a number, it means you're taking the graph of f of x and you're moving it down that many units. So if you have a point xy on the function f, if you moved it down that many units, it's the y-coordinate that changed. So think about it. If I have a point right here, it's on a graph, let's say like this. If I take this function and move it down, it's only the y-coordinate that changed. The x coordinate stayed the same. So this is what this is saying right here. When you do a vertical shift up or down, the x stays the same. It's just the y that changes. So if you have your regular function f of x equals, just f of x, this blue one, if you add c units to f of x, you're going to obtain another function, which is just f of x plus c. So, and then if you have the same function f of x, and if you subtract c, then you're moving the graph down c units. So let's see an example. All right, so our parent function is the absolute value function, f of x equals absolute value of x. I don't know if you can tell, this is black, this is green, and this is blue. So a new function, absolute value of x plus 3, is just going to be your absolute value function moved 3 units up. So this moved 3 units up, and if you follow this point, it also moved 3 units up. So originally this point was 1, 1, and when you moved it up 3 units, it became, well, the x stayed the same because you just moved it up, and you added 3 to the y value. So this will be the 0.14, which is exactly the case here. And then the function absolute value of x minus 4, you just take the absolute value of x and you move it down 4 units. So for example, the 0.00 now, what did it change into? Well, the x stayed the same because you didn't move it to the left or to the right. It was just up and down. And the y was 0 and you moved it down 4 units, so the y is negative 4. So a vertical transformation, it's a rigid transformation. It takes this graph and it even moves it up or down. It doesn't change the shape of the graph. I can continue. The shape of the graph is exactly the same. Another example, if you have square root of x, square root of x plus 2 is just going to be the graph shifted up 2 units, and square root of x minus 3 is going to be moving square root of x down 3 units. All right, so we move the function up or down. Now we move it to the left or right. So this is called a horizontal transformation. We're moving the function horizontally. So now, how does that happen? If c is added to the variable of the function, so not outside of the function, so vertical, you had f of x plus c. Remember that f of x is the y, so it was the y value that got c. That's vertically. Now horizontally, it's the x value that is going to get moved now. It's going to be moved to the left or to the right. So if you add a constant c to x, then the graph will be moved to the left that many units. So let's think about that a little bit. So on the side, let me go on the side down below here. If I have the graph of absolute value of x, okay, what is the x-intercept right here? I know it's 0. What if I want the graph of absolute value, what if I want the graph of absolute value of x plus 2? Okay, so I'm adding 2 to the x. Where is this going to move? So where is the x-intercept now? X-intercept of this one, where is it going to be? Well, I know that to find the x-intercept, I have to set the y equal to 0. So to find the x-intercept, I'm setting n equal to 0 and solving. And the absolute value of a quantity is 0 when that quantity is 0. So x equals -2. So the x-intercept is going to be at -2 now. So this corner right here moved to the left 2 units. So when I add 2 to the x value, it means moving to the left 2 units. So it's a little backwards than what we're used to, but this is the reason why. When you're adding something to the x, that means that it moves to the left. Because think about this one. To get back to where I started, I would have to add 2. So that's why for horizontal shift, when you're adding a constant to the x, it moves to the left that many units. And if you're subtracting that constant from the x, then it will move to the right that many units. So in general, so when you do a horizontal translation, notice that the y value stayed the same, like the graph stayed the same. I didn't move it up or down. So it's the x value that changed. So in general, horizontal translation means that every point xy on the graph of f of x is transformed to x minus the constant and y stays the same, or x plus the constant and y stays the same, of the graph shifted to the left and of the graph shifted to the right. So this, as long as you remember that this is exactly backwards, you'll be fine. So let's see. So when you subtract the constant, you're moving to the right, and when you add the constant, you're moving to the left. So if you have your graph f of x right here, to get the graph f of x minus c, you move the whole graph to the left, to the right, I'm sorry, to the right. So let's say if this was x, this is going to be x plus c. And then if you have the graph y equals f of x, and you add the constant, it means that it moves to the left that many units. So if this is x, this is going to be x minus c. So let's look at an example, 2 examples. So I have f of x equals x squared, our parabola, the parent function is x squared. And if I want the graph of x plus 3 squared, so what did I do? I added 3 to the x, so it's x plus 3, everything squared. Then that moved the graph to the left. So remember, when I add, it means to the left. And if I want the graph x minus 2 squared, I subtracted 2 from the x, it means I moved to the right 2 units. Now, if I have f of x equals square root of x, and if I want square root of x minus 2, I subtracted 2 from the x. That means I moved the graph to the right. And if I wanted the graph of x plus 4, I added 4 to the x. So that means I moved this one to the left 4 units. So this is a horizontal transformation. It's still rigid. I'm not changing the graph. I'm just changing its location. And then I'm changing it horizontally, which means the x value is going to change, opposed to vertically where the y value was changing. So the last type of rigid transformation is reflection. So you can have a graph, let's say f of x is this one, and the graph negative f of x is just going to be the graph of f of x reflected by the x-axis. So if the y value if the function itself is multiplied by -1, this is what it means, negative f of x. If the function is multiplied by -1, then you have a reflection over the x-axis. If the variable itself, so if I have f of x and I want the graph of f of negative x, if the negative goes with the x, not with the y, not on the outside, not with the y, then I have a reflection over the y-axis. So this is the graph of f of x. The graph of f of negative x is going to be the reflection over the y-axis. So what happens in here if I have a point xy on the original graph? Then what is the point becoming when I have reflection over the x-axis? Does the x location change? No, the x location stays the same. So the x coordinate stays the same. It's only the y that changed. The y was something here, and the y is its negative counterpart. So negative y. So when you do reflection over the x-axis, the x coordinate stays the same and the y changes. When you do reflection over the y-axis, if I have a point xy on the function, when I reflect it over the y-axis, notice that the y-coordinate stayed the same, but the x changed from this positive x, whatever it was, to its counterpart, negative x. So this right here became negative x and y. The y stayed the same, the x changed. So examples of reflection, if you have the absolute value function, f of x equals absolute value of x. If I put the negative on the outside, so if I want to graph negative square root of x, I just reflect this over the x-axis and I get it. If I have square root of x and I want to get the graph of this, there's a typo in here, so this should be negative on the outside. So typo, fix that in your notes. So if I have the graph of square root of x, to get the graph of negative square root of x, I just reflect square root of x over the x-axis. Now, if I have the graph of x cubed, and I want the graph of negative x cubed, then I just reflect the graph of x cubed over what now? The negative is with the x. It's not, well, in this case it happens that it's going to be the same thing. It's not negative x cubed. It is negative x cubed. But these are the same thing. So in this case, if I reflect this portion over the x-axis, I get this. If I reflect this portion over the y-axis, I get that too. So this, it's because this is an odd function and it has symmetry with respect to the origin, if that rings a bell. But if I have the graph of x cubed and I want the graph of negative x cubed, I just take this graph and reflect it over the y-axis. So when I reflect this portion over the y-axis, I'm going to get it this. And when I reflect this other portion over the y-axis, I'm going to get this other portion. So this graph right here is negative x cubed, which happens to be as the same as negative x cubed, and which means that I would get the same thing if I do reflection over the x-axis. Okay, and then last example, if I have f of x equals square root of x, and then I want the graph of square root of negative x, now you know that since the negative is with the x, that this means reflection over the y-axis. So I just take this portion and reflect it over the y-axis, and this gives me the graph of square root of negative x. So look at these and make sure this makes sense. So vertical translation means up or down, only the y value changes. Horizontal translation means to the left or to the right. Only the x value changes. And then reflections, you can have reflections over the x-axis where the y value changes. And then you can have reflection over the y-axis where the x value changes.